It's a pleasure to introduce Martin Copic, and he's going to talk about work with lots of people, some of whom are from Southampton.
Yes. Well, first, let me thank the organizers for having me here. It's really a great pleasure. And secondly, I feel a bit awkward. I mean, this is going to be completely experimental work, rather orthogonal to the mathematics we've been hearing mostly. So please bear with me. Some time ago, Jeffrey and Rachel Toffin and Owen Parry contacted us whether we could measure by light scattering some elastic constant in this interesting materials, and of course we said yes, and this is how we got to this work. So, and I think it's a rather interesting situation. We have a new transition to a modulated nematic phase, which shows interesting modulations or textures. And this has been observed by several groups besides our group. Also, John Goodby and Helen Gleason and their co-workers have found similar phenomena in similar materials, and Vich and his group in Dublin, they also observed in this new phase, but they have a very different explanation, and I will say just a word about it. So I would first like to present this new phase and then show how nematic fluctuations and dynamic light scattering can tell us something about the elastic properties of these materials. And so then I will present the results and some analysis of the results, but I must say that at least as far as I'm concerned, what is really happening is still very poorly understood, and I will draw some conclusions. So this new nematic phase is very interestingly observed in several materials, which are actually sort of dimers of very usual nematic materials. In particular, what we've been working recently, and which I will mostly present, is the old CB cyanobiphenyls, but not just the Turing structure, but the two cyanobiphenyls linked by a flexible linker of different lengths. And so and these materials show first a usual nematic phase, but then at some point several of them go into a rather different strongly modulated phase, and modulation really depends also on sample thickness and so on, so it doesn't seem to be an intrinsic property of the material. So the second point is that in some 11 years ago, Ivan Dozov proposed that, quite just theoretically, that if it would happen that the band elastic constant would become negative, then of course this means that there must be an instability, and he analyzed in a very simple model this instability and showed that the result of such instability could be a phase which is sort of akin to a cholesteric phase, except that instead of molecules being perpendicular to the helical axis, they form some angle with the helical axis. That means that you have both bend and twist present. Also, so the group of Professor Vich in Dublin also observed this kind of modulations, and they suggested that in a very similar material that we've been involved with, that this modulated structure is due to a softness, or actually negative value of a combination of splay and twist elastic constant, but as I will show, I think this is wrong. And the last point, which actually I think got Jeffrey Luckhurst thinking about that Dozov's paper is relevant, is that Alberta Ferrarini, some years ago, when she was doing her calculations, if you remember what she does, she does sort of mean field simulations, but taking very detailed account of the molecular conformations and some contact van der Waals interactions, but then uses mean field, which sort of imposes the nematic structure on the system, and then she calculates the elastic constants, and in some simulations with this with dimers she gets negative band elastic constant, which of course means the instability. So when you observe these materials under cross polarizers under polarized microscope, you at some point, as you cool down from the usual nematic phase, you get this rather intricate striped patterns, where the period is approximately the same as the thickness of the sample, and with somewhat thicker samples, this rather regular structure, which you get with the thickness of the samples of a few microns, degenerate into a more or less messy network of something that looks like, I will show it a little later, network of disclination lines. So
Sorry.
Yes.
Can we go back to the? So those look like some kind of smectic or some kind of layered. It looks like some kind of.
No. This
is the top view.
This is top view of a texture, and this is just modulation of the optic.
Right. No. I understand. that. But
it's more akin to fingering, to the fingerprint texture of cholesteric. This is how I understand it. I would say a few words about it. But this more irregular structure that forms, I will show the picture in a few seconds. So the structure that was proposed by Dozov as a sort of when band elastic constants become negative, of course you cannot fill the space with a homogeneous band. So the two possible homogeneous, pseudo-homogeneous, but that means modulated structure, but which are still on a large scale homogeneous throughout the sample, are either combinations of bend and splay on the left or bend and twist on the right. Now he also analyzed this in a very simple model, taking the usual kind of Frank free energy and added, so assumed that the band elastic constant is negative, so that means an instability, and I have to stabilize it with higher order terms, and he assumed these three terms which give you in Fourier transform q to the fourth power contribution, which stabilizes the modulation at a given value. Now, I don't know why he used second derivatives. I think it's ugly, but it probably doesn't matter so much at this level what you use as a stabilizing terms. So when you analyze this kind of simple free energy, then you get that the amplitude of the tilt of this structure, this tilt with respect to the axis of the structure, is finite as the as k becomes negative. You get the period of the modulation and the value of the free energy. Now k3 to the third power is negative, so this is a negative value compared to the undeformed nematic state. So this is then the stable state, and you get a twist bend state with also with somewhat different free energy. And if k1 is larger than 2, the splay constant is larger than twice the twist constant, which is usual in usual nematics, then the twist bend phase will be stable in this simple model. So one shouldn't really take this too seriously, I guess. So now when we look at microscope observation of what happens, no, this is now a small, short movie just showing it doesn't really, there's not enough constant, but anyway, you get to a transition which we can sort of determine, and somewhat later, maybe a degree or so, and a few seconds or a minute later, then you get this striped texture that forms. This is in a rather thin cell, now in a somewhat thicker cell. Yeah, come on. No.
So again, we've got cross-polarizers, yeah?
Yes. Of course. Yeah, sure.
Just check.
So in a thick cell, try to show. Again, this is you first start with a quite homogeneous nematic phase, but the first thing that appears is some faint domains, which are probably domains of opposite chirality of the. This is how we explain it, of opposite chirality of this helix. Now, I should mention that measuring chirality in presence of birefringence is optically nearly impossible. You can do it in very clean quartz crystal, looking exactly along the optical axis, but otherwise it's impossible because chirality is, optical activity is a much smaller effect than birefringence. So, maybe I should comment at this point with deuterium NMR spectra. Actually do show that there is some symmetry difference between these two domains, which Jeffrey Luckhurst interprets as the signature of the opposite chirality. But one should actually be a little bit careful with that, because deuterium NMR actually measures a second-rank tensor property, which is by itself insensitive. It is sensitive to changes of symmetry, but not to, in particular, to changes of the sign of chirality. So this is already in this low temperature phase, but there is still no modulation, and only a little later, if you wait a few, let's say a few tens of seconds, and you decrease the temperature a little bit more, then this modulation appears, and with a thick cell, it is much more irregular. It's obviously a sort of an array of disclination lines which meet at certain points, and sometimes it's really a very irregular sort of network of something like disclination lines. Yes.
There's nothing in the material to prefer right-handed to left-handed.
No, in principle, the material is achiral. That's the if this is true, this is again another, if the interpretation is correct of this twist bend phase, then this is another case of spontaneous chirality breaking, like in the bananas. And there are, as I will comment, some similarities in these materials with the banana phase. The molecules are sort of like flexible bananas, but they can flex either way. So in order now to check this, what is happening, we wanted to measure the elastic constant by light scattering. Elastic constant are usually measured, and I will report a little bit on that too, by Frederick's transition measurements, but that is not really very easy to do, and it's also not very reliable in my opinion. So by light scattering, we of course observe nematic director fluctuations, and the relaxation rate of the fluctuations gives us ratios of the elastic constant to viscosity. This is a very standard thing. Now the scattering intensity is proportional to the optical anisotropy divided by the elastic constant. So if we measure the amplitude of the dynamically scattered part of the scattered light, we can get the ratios of the elastic constant to the order parameter squared. Now this is actually what enters the lowest order terms in the elastic coefficients in the Landau Ginzburg expansion in terms of the tensorial order parameter are exactly these ratios of the actual elastic constant divided by the order parameter squared. So in a sense, these are quite interesting quantities. Now, as you well know, nematic fluctuations can be decomposed into two branches. One is a splay bend and the other one is twist bend branch. And so the relaxation rate is given, as I said, of all the fluctuations by the ratio of the elastic constants to some viscosity, and the amplitude through equipartition theorem is simply kT divided by elastic constants times the wave vector magnitude squared. So more precisely, the relaxation rate are given by this kind of combination of either splay or twist constant plus bend, depending on the direction of the wave vector divided by some effective viscosity, which is a combination of all the Leslie viscosities. And the only thing that perhaps is worthwhile taking out of here is that in twist, you only have the rotational viscosity. So no decrease of the viscosity due to backflow. In splay, in pure splay, you get a decrease due to backflow, which is rather small because in usual materials alpha 3 is considerably smaller than alpha 2. So the strongest contribution to backflow you usually have in the bend fluctuations. Now, of course, choosing different directions of the incoming and scattered light and different polarization combinations, you can actually choose precisely which fluctuation mode you are looking at. Now, this is how our samples, the two pure compounds that we were looking at looked like. So it's essentially cyanobiphenyls linked by a methylene linker and another cyanobiphenyls, and this part is quite flexible, and we looked at about two compounds with 7 and 9 carbon units in the chain. The cells were in a usual planar orientation.
What's the range of stability of an ENX?
It goes all the way down to the crystal face.
So there is no smectic actually.
There is no smectic face, no.
And that means 20, 40 degrees? What's
I forgot what's. Yeah, it's something like 20 degrees.
Does it increase with X increasing?
A little bit, yes. As you see, but not dramatically. I will actually show a mixture which may be. So now the first thing is from the relaxation rate we get the ratios of the diffusivity. This is the ratio of the elastic constant to the viscosity. So this is essentially like a diffusion constant. So this is why it's called diffusivity. And you can see that you get usual kind of behavior for the splay and for bend, while for twist, while bend very strongly decreases. We were sort of rather surprised to see such a dramatic effect initially. But one should be a little bit careful, of course, because here you also have the contribution of the viscosities, and in a simple nematic, what you expect is that elastic constant are proportional to the order parameter squared. The rotational viscosity is also proportional to the order parameter squared. So a constant diffusivity is something that you'd expect in a usual nematic. But so here is the still strong. If we have to.
Sorry, Martin. What was going on with the divergence of the green
yeah.
line?
Yeah, okay. This is, I wanted, yeah. I forgot to know that. We get also some signal, rather strong increase in the diffusivity of the splay mode, what was splay mode in the clean nematic phase. As we enter this new phase, let's tentatively call it twist bend phase, because we strongly believe that it is.
That's not a crystal.
That's not a crystal. No. No. This is clearly nematic phase. Why we know it's nematic phase? First of all, we can still see strong fluctuation. This is just part of it. Then you can X-ray scattering that was done by Rob Richardson clearly shows that it is still a nematic phase. It is perfect signature of the nematic phase. So the same goes for the other compound. It's a very similar behavior. Now, through looking at the amplitude of the scattered correlation function, we can get, as I said, the ratios of the elastic constant to viscosities, and again, this elastic constant to the order parameter squared. So this is the bare Landau-de Gennes elastic coefficients. I will have to say a little bit more about that later. And you see again that the bend, in both cases, the bend decreases very dramatically, while the splay and twist remain approximate, just slightly increase. I should also comment on why they are all equal at these values at the nematic to isotropic transition. In principle, by looking at absolute intensities, we should be able to measure the absolute values of the elastic constant. But determining absolute scattering intensity is more or less impossible. It's very difficult. So we only have, for this particular compound, relative values, because in Southampton, where they measure by usual Frederick's transition technique, it's difficult for them to measure at high temperatures. We have some very recent measurements of the Frederick's transition that we've done ourselves, but they're not complete yet. So we can only show now the relative values relative to the value at the nematic isotropic transition, where we expect that the nematic is approximately behaves like a normal nematic. So this is just the same thing shown in linear scale again. We even also in the scattering intensity data, we get this dramatic increase in the apparent, I should say, elastic constant of the splay. I have no good explanation for that. I will comment a little bit on the end what perhaps is happening. So again, in the linear scale, you can perhaps a little better see how the nematic constant here decreases in CB9, CB by something like a factor of 5 from the isotropic to the minimum in the nematic phase. But very interestingly, in all cases that we have looked at, it also just before entering into this this here is the transition to the twist bend phase, it increases again. Again, we have no good explanation for that. Again, I will comment a little later. Now, of course, it's also interesting to look at the true elastic constant. And so that it means you have multiplied previous data by the order parameter. We got the order parameter by measuring the optical anisotropy by polarization interference. And so we take this data and then multiply the light scattering data by the square of the optical anisotropy. So this is then proportional to the actual bent elastic constant. And we get this funny curve. The increase is what you'd expect, initial close to the nematic to isotropic transition due to the S-squared dependence of the elastic constant. But then this negative trend takes over. But then it stops again a degree or two below the transition to this twist bend phase, and then it increases again. This is this funny increase that we always observe. All the elastic constant, so this is the same as before. But here you also have splay, and splay is the black one, and twist is the green one. They obviously behave a little different with temperature, but we can't really comment on that. The actual, for the ratios of the, from very recent, I actually got a few days ago from Ljubljana, our Frederick's measurements, the actual data ratios of the splay and bend are probably quite correct in this picture, while twist is certainly considerably smaller than what you see from the other two at the nematic isotropic transition. That's all the data are taken in the normal nematic state. We cannot measure in the modulated phase because the scattering on this texture is high, much too strong to allow us to do any reasonable measurements. So essentially, what we think we are looking at, this is the conclusion, is some kind of a soft mode of the transition to the twist bend phase. And if this would really go linearly extrapolate to the transition temperature, then I'd simply say, yes, this is a soft mode, and we're done with it. This upturn just before the transition is something that you don't see in usual, in this generic soft mode. So now, we have been also looking at a similar system, but which is even sort of more pronounced all this phenomena. And this is a mixture that was prepared in Southampton of 4 dimers with ester links, not simple links like before, with some addition of a fluorinated version of CB9CB. The pure fluorinated version of CB9CB, this is at this end of this phase diagram, has a narrow nematic phase and then goes to this twist bend phase at rather high temperature. But while this Ka mixture of the dimeric esters has no transition to the modulated phase because it crystallizes before. But as you mix with this CBF, 9CBF, then the transition temperature to the twist bend phase goes down, and so these are then the same kind of measurements, but with the exception that here we have reliable data. Well, we have relatively reliable data from Frederick's transition measurements, and you see that splay again behaves like in previous cases, and it's quite a bit above both twist and bend constants actually, even at the close to the nematic isotropic transition, the smallest one, which is very unusual. Usually the smallest elastic constant in usual materials is the twist constant. Bend is usually actually even the largest.
Is M and X phase transition first order?
It is, yes. By measurements, it's slightly first order, yes.
Measurements you mean by DSC?
Yes. There's no theory actually, so yeah.
And the fluorinated compound, which parts are fluorinated?
I actually have a picture. Not too much. This is one of the components of the Ka mixture with the ester link, and this is the fluorinated CB9CB. And in this, so when you look in detail at the bend constant in this mixture, this is the true bend constant here. Actually, it decreases by something like a factor of nearly 10. So this is a very dramatic decrease. But even then, it still has this increase just before going into the modulated phase. The elastic constants as measured by Frederick's transition look quite similar, except that at the minimum value close to the transition, we get something like 0.6 piconewtons, and light scattering gives us 0.3 piconewtons if we take the same values at 60 degrees. So there is some discrepancies between Frederick's transition measurements and light scattering measurement, but I've been analyzing some of these Frederick's transition measurements yesterday, and I think this is due to the peculiar nature of these phases. Very small band elastic constant can actually be rather poorly determined from Frederick's transition measurements. So this, I think, is just an experimental discrepancy. Now, you can sort of do a little bit more analysis of the data. This is, of course, it is well known that to the lowest order in Landau-Ginzburg expansion in the tensorial order parameter, splay and band elastic constants are equal. So you need to go one order higher in order to remove this degeneracy. And in the cubic invariants that contribute to the bulk elastic constant, there are actually 3 of 9 or 10 of them that do that. So these are the 3 ones. And when you then express the cubic contribution to the splay bend and twist and bend elastic constant in terms of this of the coefficients of this invariant, you get something like this. And so since there are 3 new constants and 3 measured elastic constants, we can actually sort of say something about these cubic coefficients. Now, so when you plot now these ratios of the elastic constant divided by the order parameter squared, so this is actually what we get directly from the scattered intensity measurements, as a function of the order parameter, or in our case of the optic index of refraction anisotropy, you get that the slope of the lines is then the cubic proportional to the cubic contribution to the elastic constant, and the splay and twist elastic constants are just slightly increasing. So that means that this cubic contribution to splay and twist is small and positive, but it's actually insignificantly. When you do the fit, it's hardly significant. While the bend contribution, the slope of the bend line, is strongly negative, and this in both compounds. So what it says is that this C1 coefficient of the cubic invariant is negative. Of course, that means that in order to stabilize the free energy, you need to add higher order terms.
Do I understand correctly? Do you have K1 and K3 nearly degenerate?
No. They would be degenerate if you didn't. There wouldn't be. This is theory.
Yeah, it's there.
I mean, measured.
Measured. I mean.
No. Measured are very different.
I mean measured, not
measured. K1 and K3 are that different.
Okay. So that means even at the level of S squared, Landau divergence does not work. And
No. Yeah, this doesn't mean that.
It means because K1 equals K3 at the level of S squared. If you do just...
No, but we measure everything.
I know, experimentally you see the difference, but I mean at the theoretical level, there is a disagreement with the S square dependence.
Yeah, that's why he's taking the cubic invariance, isn't it?
Yeah, of course, the actual dependence of the elastic constant is not s squared. Is it s squared plus s to the third?
No, but
What we measure is k over s squared.
you also have K1 not equal K3 at the level of S squared,
No.
theoretically.
Yeah, theoretically.
In lambda Uderzen's theory, K1 equals K3 when you consider only S squared terms.
Yes,
But this is the same thing.
That's what he's saying.
Yeah.
That's the same thing.
He's looking for the difference and imputing that to the cubic term.
Yeah, more.
Right.
So those
Don't
curves that you
argue
showed
whether
us,
it's true or not.
did you get those by fitting?
Yeah.
Then I have a question regarding this, what you have here, because C3 seems to give the same contribution to all three constants.
Yeah, but
Oh, it does
yeah, of course,
like
yes,
that.
you're right.
So you can't get
We
C3.
fit, if you now calculate from the slopes, from these slopes of these curves, what are the values of the C1, C2, and C3? You get the C1 and C2 are C2 and C3 are approximately within our accuracy 0, very small, and C1 is strongly negative. In some relative values, again, we have no absolute values, but relative values, C1 is minus 10, and C2 and C3 are 1 plus minus 1, something like that. So the C1 invariant is strong, is negative, and enough negative that the actual value of free energy at the order parameter or something like, we don't know what is the absolute value of the order parameter, but in your usual nematic, if you go deep down into the nematic phase, it will be something like 0.6, 0.7. So this point should correspond to something like the actual two-order parameter of something like 0.7. That's I'm guessing. So now so what we can say then is that this transition to this modulated phase is sort of driven by the increase in the smectic order, in the nematic order parameter. This is sort of an interesting and intuitively understandable thing, because as if the molecules are more in sort of more highly arranged or oriented in the same way, then this fact that they're easily bendable should become more sort of apparent. This is very hand-waving argument, but it's also interesting that the same thing is happening as you go from a nematic to the smectic A phase. You also have this smectic A order more or less driven by the increase in the nematic ordering. And this perhaps has some relevance. So the main problem that we see here is that why the band constant increases just before this transition to this modulated phase. So maybe some indication of what is happening may come from the usual band core, stiff band core molecules. Usually they don't even form a nematic phase, but when they do form a nematic phase, it is known that the band elastic constant is also small, and but they always go then not to this twist bend phase, but to the smectic phase. So perhaps in this flexible dimers, we have something like a competition between this smectic phase and this twist bend nematic phase, which then drives this small increase in the bend elastic constant. This is pure speculation. I have no serious sort of argument to base that.
Let's see, maybe a stupid question, but when you say that the bend constant increases, it means that it changes sign?
No. Just instead of, in a naive theory of the transition to this modulated phase, if it would be second order transition, you'd expect that it goes all the way, the band elastic constant goes strictly to 0, and then you get transition to the new phase, true soft mode.
Okay.
But of course, since it's known that it's slightly first order transition, you don't expect it to go all the way to zero. So this is fine that it doesn't go all the way to zero. What is a little bit odd is that it actually has this small upturn, like perhaps most nicely visible in this plot with respect to the order parameter. You see, it's quite linear down to this value, and then it has this shoot up just before the transition. Which, let's say, you could say, perhaps it is due to some incipient smectic fluctuations, because in the smectics, of course, bend is being expelled.
Well, we know permittivity data.
This is permittivity data.
Okay, but there are known permittivity data where you have, let's say, for nematic smectic, exotic smectic phase transitions, that you have this final upward behavior. And then
in the smectic, this is well understood, because in the smectic, bend is forbidden, so you expect and you have this pre-transitional increase in the bend elastic constant.
Yeah,
what I'm arguing here that this is
I don't mean bend, I mean some other elastic.
Oh, yeah, okay.
They may have this funny behavior close to the transition, even though when you cross the transition, they drop down.
Yeah, but then this would be what one would call this higher order effect in a Landau type of theory, where different things can happen to elastic coefficients, the way depending on how they couple to the order parameter. They are not the primary susceptibility. Here, I'm trying to argue that this is the primary, the soft susceptibility, which shows this unexpected increase. So this is actually the end of it. So anyway, it is obvious that there is the phenomenon of this new nematic phase, which let's suppose it's this dorsal twist bend phase, is driven by a softness of the bend elastic constant, not the splay or twist as proposed by Vich's group. But I still think there is lots to be understood about the phase. So, thank you. Yes.
Do we think that there is a significance between the difference in the Friedrichs measurements and in the light scattering measurements? I mean, is that something that just comes because you never quite get the same thing, and blah, blah, or is that, could it be that actually there's some different physics going on that one?
I have an idea that there could be an actual physics behind it, and this is it. It could be, since this is a modulated phase, you have a critical wave vector at which the phase transition happens. This wave vector should be of the order of mesoscopic scale. That means the nanometer range.
Just on the basis of your experience as an experimentalist, rather than on the basis of theoretical speculations, because I want to make some other theoretical speculations in it. But on the basis of your experience, because you've done loads of
this is precisely what I'm about to say.
Yeah.
So when you go from a homogeneous to modulated phase, you actually expect that the soft mode is going to go soft at the period of the modulation, not at zero wave vector. And this, we have actually done experiments seeing this in the case of going from the smectic A to smectic C star phase how many, 20 years ago, or even more. That we saw by light scattering that the soft fluctuations happen at the wave vector corresponding to the helical twist. So here, in principle, since it's a modulated phase, you'd expect the same thing. And Friedrichs transition measures at zero wave vector. We measure at a finite wave vector, which may be closer to the soft wave vector. So so this is perhaps one possible explanation, which was incidentally also could explain this upturn, because the soft wave vector could be a function of the order parameter or temperature also. So you're actually at some point, you could be at the minimum position in the dynamic scattering
So your
function.
statement is that the fact that we've got a finite QC, right, is the key to it being a first order phase transition.
No.
All right.
No. Is the key for our observation that at zero wave vector, that means in Frederick's transition, you see a higher value for the elastic constant than in light scattering, and that in light scattering you don't go all the way to zero, but before going to a small value you get a small increase. This could be explained by the wave vector dependence of the the measured susceptibility.
Could I sort of rephrase that? What you sort of are saying is that we've got a critical modulation, right? What you actually want to measure is the energy associated with the oscillation at a finite value of Q, and that measuring values of capital K are in some sense only surrogates for measuring the, if you like, the energy gap between the fluctuation, the energy associated with the fluctuation of finite Q, and as a result, you aren't picking up something that is active. I mean, is that what you're saying?
No, well, we are measuring susceptibility. So you're measuring the second derivative of the energy with respect to.
See, what I'm looking for are things that can drive soft mode transitions from being continuous to being first order, right? I mean, you know, I have a tool bag of.
There is the nematic or smectic transition is driven first order by the fluctuations. So.
Well, but it can be driven even in mean field theory. It can be driven first order simply by the coupling between the order parameters.
Yeah.
Right. By the fact, in some sense, that you've got two order parameters.
Yeah.
Right. So, I mean, there are two things that I can think of that could drive some kind of apparently soft mode transition first order from right. One is the coupling to another hidden order parameter. Right? I mean, if you've got another hidden order parameter, you can drive a continuous first order transition second order. And the second is that we've got a modulation, and if we had a two-dimensional modulation rather than a one-dimensional modulation, then it's always possible, because of a Q1 plus Q2 plus Q3 equals 0, to have a third order term. Right? I'm looking for things that will either drive my second order, my fourth order term negative, in order that I have a sixth order term that stabilizes in some kind of Landau theory, or give me a third order term that I might not otherwise have expected to get. Right? So giving me a third order term is because I have some more complicated structure, right? And a hidden order parameter is something that drives my fourth order term negative and gives me the sixth order term,
right? Maybe I should make another conclusion. There are two problems. One is it really the twist bend phase that is the underlying of this phenomena? If it is, then one has to answer the question, what is then this strong texture that you get in all cases just immediately below the transition? This texture is obviously not intrinsic because it depends very strongly on the properties of, let's say, how you prepare the sample, of the thickness, and it is regular at small thicknesses. It's quite irregular when the thickness of the sample is large. And my sort of hypothesis is that in a neat twist bend phase, you have bend which is favorable, but you also have to introduce some twist which sort of then introduces some frustration. And perhaps then you can relieve some of this frustration by again deforming this twist bend face into this texture, but I've been thinking about it, but haven't really gotten very far yet. So.
I further comment on what Tim just said about this hidden order parameter which might play a role here. But I mean, the culprit or the natural suspect would be the angle between the two dimers as further order parameter. Is there any NMR data, for example, that would distinguish between the arrangement on average of the two dimers and the two phases you have considered?
Not well, in very sort of indirect way, perhaps, because what the NMR data says that two deuterons that are equivalent in the nematic phase become inequivalent in this deformed phase.
And could be suggestive of the angle between the two, which is not.
I think that it is only suggestive of local biaxial symmetry, which could, of course, be due to the local spontaneous bend of the constituent molecules.
Your opinion would be that elastic constants in Mx are positive, right?
Well, the actual elastic constant must be positive.
So actually,
but the actual elastic constant have to be redefined with respect to the new ground state.
State that you are studying. That's clear. So actually, this Dozov's idea wouldn't.
Well, it's all right. You just have to rephrase the words. I mean, as you get to the new state, you have to define new elastic constants.
Have you looked at Dozov's model and taken it to take it seriously and turn the handle? I mean, if you take Dozov's model and take it seriously, it predicts a continuous phase transition, does it?
Yeah, but he has taken invariants which are, I mean,
yes, you can take it seriously, but no, you shouldn't take it seriously.
That's what I think, yes.
There's no phase transition, does it?
The fact that we have first order phase transition means that the symmetries of the phases should somehow.
No, not necessarily. Not necessarily. I mean, like I said, if you've got a hidden order parameter, you can manage to.
Well, actually, if you have cariality in non-carial systems, then just for first principles, you need higher order parameters like, third rank tensors.
It's not chirality.
There is. If the hypothesis of the twist bend phase is correct, then you get spontaneous chirality breaking from the non-chiral nematic to the two opposite chiralities of this twist bend phase. It's actually a generalization of the cholesteric phase, with the molecules going, instead of this way, going around this way.
But you get both states.
Of course. We see domains of. We see.
No, there's no intrinsic.
There is no intrinsic chirality. It's spontaneous phase chirality.
Within the sample. So we have both chiralities coexisting.
Yeah, of course.
It is not intrinsic.
No, but light scattering would see that.
I don't know what you call intrinsic. Molecules are, of course, not chiral, but the phase, if it's true, it's intrinsically composed of two domains of opposite chirality.
And the two states have the same energy.
Yeah, of course.
And that would square with what you say about six cells. When you look at the transition, you get probably lots of different domains, and that
we think we see the domains, but then very soon, that means in half a degree and in minutes, this complicated structure forms.
What about adding very small, very, very small amounts of a chiral twisting agent next to the chirality, so you can break that symmetry?
It's an interest. We've thought about that. It hasn't been done yet.
When you have about one of these band faces, display band picture that you showed? How many molecules, how many of these bananas it takes for a cell period?
Depends on the size of this of the parameters of this quartic terms that Dozov introduces. So the value of this fundamental period is given by the ratio of the actual band this band coefficient divided by the C1 plus C2 is the C. And you don't know what is C1 and C2, but it should be something mesoscopic, of the order of nanometers.
So what is the size of the molecule?
The size of the molecule is maybe 3 nanometers, something like that.
Did you mean mesoscopic nanometers? Surely you observed it to be microns.
That's exactly my point. That the period that we observe in the texture depends on the thickness of the sample and has nothing directly to do with this period.
Yeah.
It's actually wrong.
Thousands, I think.
Okay. Now another question. I don't know if you look at this kind of experiment, but what would happen if you were to apply an electric field? How would this get straightened out if it did? It becomes would still see a.
This has been done. You can straighten out the structure. But this.
What happens to the phase transition, though?
I don't know what happens to phase transition under field, but it shouldn't have much because you shouldn't be able to do much to the phase transition because in all cases of the nematics, it's well known that in order to induce thermodynamic changes in the phase transition, you need enormous fields. This has been done many years ago by Lehidis and Georges Durand.
Well, that's nematic to isotropic, whereas I guess
it's a secondary transition.
Yeah.
But still, I don't know. I don't know the answer anyway.
But do electric fields make a difference to the blue phase boundaries? Yeah. So these are more like, I would think these were more like blue phase boundaries than, right? And if you start to put electric fields
we haven't done that yet.
In cholesterics and stuff like that, then you can unwind. And
you can unwind the cholesteric, and you can unwind this superstructure easily. That has been done by.
Right, but because the subsidiary phase involves winding, or might involve winding, I would think that electric fields it would be quite susceptible to electric fields, actually, as opposed to the nematic isotropic phase transition, where the effects are very.
Actually, from modeling point of view, I think this gives a very good suggestion on models for semi-flexible polymers.
From a microscopic modeling point of view, yes, and I would also say that this is quite a nice problem from this continuum modeling problem. You have this phase. Now calculate how can you get to this.
What were the boundary conditions for these cells?
Normal planar orientation, that means wrapped surfaces. Yeah. It's interesting that it seems to be quite difficult to produce homotropic orientation for whatever reason, but this is again perhaps not very, I don't know. In bananas, it is well known that boundary conditions are much more tricky than in usual calimitic materials. Due to, of course, to the much more complicated shape of the molecule. So perhaps, and it seems that this is the case, that to orient them, it's not as simple as in a usual calimitic situation.
Okay, thank you.
Is there any evidence of a transverse dipole in these bananas? Oh, it's too small.
You do.
Yeah, I think, well, in this simple material that I was mostly talking about, not really. This is you have strong longitudinal dipole like in biphenyls, but they're actually opposite. If you look, this is one dipole, this is the other one, but there are no transverse dipoles here.
Daniel has a question.
What's an alternative to using those second order terms to stabilize it? You showed this man's model, and are you going to put it in an order?
Well, I mean, what seems odd to me is using second derivatives on these quartic terms. I think one should use fourth power of first derivatives.
Well, actually, you could also renormalize S by S plus S0, T by...
It's just the less opportunity.
Of course.
And you should get the same effect.
Yeah, sure.
It's like a regularization of the symmetrics, the end.
Yeah. The same kind of problem, yes.
You mean an alternative to second order? Pardon?
Chooses.
Okay, the discussion seems to be kind of decaying exponentially into
Thank you, yes.
Thank you.